आ गया आ गया Sorry, Dr. Sahab, this transmission goes live on Facebook page also of Pakistan Society of Civil Engineers. उसमें जरा मुझे टेक्निकल इशू आ रहा था, ठीक हो गया इसलिए अब हम जी स्टार्ट करेंगे इंशाल्लाह। और रिजवान है Rizwan Mirza, anything goes wrong at my end, then you will be the co-host, please. Can you confirm? Rizwan, can you hear me? आपकी म्यूट पोजीशन है इस वक्त, आप बात शायद ना कर रहे हो तो मुझे आवाज नहीं आ रही।
अब क्या
जी रिजवान, आपको आवाज आ रही है मेरी?
यस यस आई गॉट इट।
ठीक है, तो आपने सुन लिया ना जो कुछ मैंने कहा है?
जी जी यस यस आई फुली अंडरस्टैंड।
थैंक यू। Bismillahirrahmanirrahim. In the name of Allah, the most gracious and the most merciful. Ladies and gentlemen, Assalamu alaikum. Good morning and good afternoon. From Pakistan Society of Civil Engineers based in Lahore, Pakistan. A very warm welcome to all the participants who have joined us on Facebook. This is lecture number 53, organized under the auspices of Pakistan Society of Civil Engineers. Today's lecture is continuation of the series of lectures that PSCE holds every month for the benefit of our young and experienced civil engineers. And our endeavor is to keep you updated with advancing knowledge of different disciplines of civil engineering. Before I introduce the speaker and the topic, I am duty bound to spell out the rules of this webinar as per instructions given by Pakistan Engineering Council. First, all the registered participants for SCPT points have to appear live on webcam. However, for the ladies, there is an exception. They have a choice to cover their face while appearing live on webcam. During the lecture, microphone of all the participants except that of the speaker shall remain in mute position. Questions during the lecture shall be typed in the chat box, and at the end of the lecture, I will read out the questions for the guest speaker to answer. No live questions asking through microphone shall be permitted, as this privilege has been withdrawn by the order of BOD, Board of Directors of Pakistan Society of Civil Engineers. Participants on the Facebook can also type their questions in the chat box, and one specific person from our society is monitoring Facebook, and any questions that will be asked, inshallah, the speaker will answer them. Ladies and gentlemen, it's my privilege and honor to present to you Dr. Hassan Tariq as our guest speaker today. And his topic is Seismic Risk Assessment of Structures. First, his education, he got his undergrads from NUST Islamabad, Pakistan in 2012. Then he got he did his graduation from Asian Institute of Technology, which is in Bangkok, Thailand in 2016. And then he proceeded to New Jersey Institute of Technology in Newark, New Jersey, USA in 2020. Dr. Hassan Tariq is based in USA, Norfolk, Virginia, from where he is going to deliver today's lecture. He is currently working for Thornton Tomasity, a highly reputed consulting company in United States of America. There he performs detailed design of structural schemes which are compatible with architectural concepts and satisfy functional needs of the buildings. He reviews the structural design of peers for compliance with codes and mentors junior engineering staff and reviews their work. Before joining Thornton Tomasity, Dr. Tariq worked in 6 private consulting companies where he gained multi-facade experience of civil engineering projects such as assessment and forensic evaluations of buildings, bridges, and other structures, analysis of structural failures and evaluation of construction defects, probabilistic assessment of structures to evaluate the expected future. I'm so sorry, the telephone call came. Analysis of structural failures and evaluation of construction defects. Probabilistic assessment of structures to evaluate the expected future performance under natural hazards such as earthquakes, wind, and flood. He has worked on flood resiliency project of New York City railway yards, where the goal was to develop cost-effective strategies to prepare the railway yards for future floods, to reduce damage to facilities and quick restoration and operations following disruption. For this project, he performed load analysis and designed the beams and columns to transfer the flood load. To his credit are 6 publications of international level and has made 4 presentations on different forums in USA and outside USA. In his short career of 11 years, he has already received 9 honors and awards. So this was a very brief introduction of Dr. Hassan Tariq. Now, Tariq Saab, the floor is yours. Kindly continue with your lecture.
Let me share my screen. Thank you so much, Pakistan Society of Civil Engineering, for having me, and thank you, Tariq Saab, for such a kind introduction. I really appreciate that. I don't know if I have achieved all much, but every day I think I'm learning, I'm trying to be a better engineer day by day. That's my overall goal. The topic of my today's presentation is seismic risk assessment of structures. Earthquake has been close to my heart for about last 10 and 12 years. I remember when I was sitting in a class of physics and professor is teaching Hooke's law, and we had a Muzaffarabad earthquake back in 2008. And the moment I showed up at home, I saw all the damaged buildings and stuff. And I looked over after it and I said, okay, just pray to God for the quick recovery and that's it. But as the time progresses, I got into the civil engineering and then a structural engineering program, and then learning more about damage control buildings and earthquakes and how important it is for the design and to improve the performance and safety. I kept on progressing in that, and you saw my master's and PhD, and furthermore, my professional kind of aspirations with structural engineering and earthquake engineering. So the topic is about seismic risk assessment of structures. As Tahir Saab has already introduced my academic background, but just a quick brief flash here that I got my PhD from NGIT, my master's from Asian Institute of Technology, and my civil engineering undergraduate from NAST Islamabad. What I do at my work, I have kind of done 3 different things. One is the structural design of high-rise buildings, concrete, steel, composite buildings, and structural rehabilitation, in which we basically analyze the existing buildings and we develop what retrofitting scheme we should use to restore its occupancy, or if client is interested in changing the occupancy from residential apartment to an office building that would change the load in some of its schemes, then we would go ahead and look at that current building and see if the change in the occupancy would be enough or in terms from structural capacity standpoint. And then the last topic is forensic investigation. That is related to the construction dispute, where 2 parties at the dispute, for example, contractor found that structural designer have designed a column or a bridge pier against seismic loading, and the transverse reinforcement is not sufficient to sustain the inelastic deformation. he would stop the construction and ask the owner for more money, and they will enter the dispute. So what forensic department does is they hire an external expert. He would review the information from both the parties, write the report. That report would go to the adjudicator, and then he will make a decision based on findings. So I have done work in 3 different departments at Taunton Tomasetti. I'm mostly engaged in the design of high-rise buildings and structural rehabilitation. So today's presentation is divided into 3 main topics. Today, I want to talk about seismic retrofitting of a soft story building, and then risk assessment of a base isolated bridges and the challenges that one could see in the high-rise buildings. And you would see the progression as we go along the entire presentation. So what is a soft story building? When we analyze the building, a moment resisting frame, let's say a special moment frame building, we basically consider infill wall as a line load, and we analyze it and we design the beams and columns. But in reality, these infill walls have a stiffness associated with that, due to which under the action of seismic loading or earthquake, you could see that there is some irregular distribution of stiffness along the height of the building. What that does under earthquake is, due to the irregular distribution of stiffness, due to the presence of infill walls on the upper stories and no walls at the first stories, cause an irregular distribution of stiffness, which will in turn turn into an irregular distribution of deformation along the height of the building. The columns at first story takes all the damage, and you could see that it turned into a complete collapse. Now, where would we see the soft story buildings? We can see the soft story buildings all around. We have commercial plazas, we have school buildings, we have residential apartments. For commercial plaza, we need first story for the parking. For school buildings, we probably need first story open for a prayer, for an assembly. For residential apartments, there are leasing offices, which are glass offices. The stiffness of the glass is much less. It's almost very flexible as compared to stiffness of the walls along the height of the building. Now, even the past earthquakes have demonstrated that the damage due to soft story was most commonly found all around the world, which means that soft story buildings are vulnerable to earthquake, and it requires special attention from design standpoint. The question is, in order to avoid the damage, should we stop constructing the soft story buildings? If we say yes, we'll probably be out of the business. Being a structural engineer, we need to understand the significance of the problem and how would we address it. Soft story buildings are there. They have to be there because we can't have walls at the first story from commercial purposes or from architectural standpoint. So these buildings will be there. Being a structural engineer, we need to determine what do we need to do in order to improve its performance under seismic loading. That's the overall idea. Now I'm going to explain you about the retrofitting process. The first step, for example, if you are retrofitting the existing building, you would go to the site, take pictures, determine the geometry of the building. The second is you formulate the nonlinear inelastic model. The third is you determine the seismic action. What that means is what is the likelihood of that particular earthquake at that location. Then you will determine the evaluation criteria. How are you checking your building model? Are you checking your building model with comparing the forces? Are you comparing the deformations? Are you comparing the strains, or are you comparing the plastic rotations? You need to define the evaluation criteria. And then you evaluate the performance of the case study building. And then you will determine the structural deficiencies. This is a very important stage where a structural engineer will determine what retrofitting approach do I need to determine. For example, if an earthquake, which has a return period of 2,500 years, and your columns only have a minor yielding, which means that they're not going to collapse under the earthquake, you can't propose an expensive or such retrofitting approach that will over retrofit the building and cause other damages. So we need to determine, And here you could see in the picture that the columns have suffered the plastic deformation. They are close to collapse, and that means you need to develop a certain approach that will either strengthen or stiffen the building, and both. Then you will design your retrofit scheme based on your deficiencies of the existing building. And then you basically evaluate the performance of the retrofitted building and you compare that with the objectives, as I mentioned earlier. And then if the objectives are not meeting, you will reiterate unless you achieve the desired objective. If yes, and then you proceed to the final report. Now the case study building. The case study building I'm going to demonstrate here, it's basically a two-story building. As you could see from a 3D ETABS model, it has an infill walls at the first stories, and at the second story only around the stairwell, and all the first story columns are left open. This building is located in the north of Thailand, just to give you a perspective that how far it is from the New York. That building, I worked on that when I was working for AIT Solutions in Thailand. I flew all the way to Chiang Rai province in Thailand and kind of looked at the existing building, and that was under construction. My question to the design engineer at that time was, if you are constructing the new building, why can't you just add a walls at the first story and make that happen and avoid the soft story? And they said, we need that first story open for the prayer purposes. All the Thai students will gather at that place for the prayer and we can't close it. Also, you could see the infill walls somewhere at the mid height of the column. That is also another topic to discuss, but you can see that it can cause hinge at that location of the column. Okay, so this is a plan view of that case study building. As you could see that we have an infill walls at the second story, we have all around the perimeter. At the first story, only around the stairwell. That is the elevation view on your right side, both the front elevations and side elevations, just to kind of get a more visuals, understanding that we have an infill walls at the second story and no walls at the first story. And then a model development stage. Now, once you gathered the information, once you gathered what is the scheme of your building, what does it look like? The next step is you would develop the mathematical model of that building. For this, I used Perform 3D. Within Perform 3D, I used a fiber-based modeling approach. In that modeling approach, I assigned a nonlinear behavior to each fiber of the cross-section. So at the bottom, you could see we have a cross-section fiber. We will discretize that cross-section into small fiber. By fiber, I mean one small square. That's a meshing language we use in finite element analysis. And then we assign each fiber the corresponding material behavior. For a rebar, we would use a part steel model. For a concrete, we have confined and unconfined concrete material model, just to demonstrate an expected performance under lateral loading. The slabs were modeled as a shell, elastic shell, which means no nonlinearity was considered. The fixed support was considered at the base. In order to simulate the effect of infill walls, I used the compression strut, which means if the load is applied in the north-south direction, this strut would be active and this strut would not take any load. And if the other way around, if the load is applied in the opposite direction, this strut would take the load and the other strut would not. So this is a compression-only struts that would take the lateral loads to simulate the behavior of CMU walls. Now, this plot shows you it's a basically very classic one. It's a pushover behavior of the building under X direction. And these markers on that curve shows you various damage levels. What that means is the first marker that is a cyan color shows that's where the concrete column begins to crack. That is expected. Once your stresses exceeds the cracking moment, 7.5 under root FC prime, you would exceed the cracking, a very lowest stress level. That's one you should expect. The second thing you would look at these, your infill walls at the first story begins to crack. The third thing is your beam at the base level begins to crack also, and then your column begins to yield. And now you would see that all the deformation, your column begins to crush, And then that's the point where column concrete begins to fall, leading to a complete collapse. One interesting thing to look at this picture is that there is no damage at the second story. There is no cracking of the wall. There is no cracking in the beam or the column, which means that once your wall crack and the columns are just by themselves, all the deformations concentrated here, and we have a typical soft story behavior. Another way to look is to validate your expected damage along the building as you exceed your drift levels. Now, this curve has also its own significance. Here I am comparing the behavior of the building with infill walls and without infill walls. This is basically to emphasize the fact that when we analyze the building, we do not consider infill walls, but when we do add buildings with infill walls, there is an increase in the stiffness, which in return will reduce your natural period of the building. And as per your response spectrum, lower period will attract more shear. And if you have a soft story building with infill walls, that higher shear demand will definitely gonna cause the collapse of your first story columns. That's another way to look into it, that the importance of ignoring the infill wall can lead to a disaster at the end. So now I'm showing you the response spectrum, which is basically came from a site-specific studies where we basically partner with seismologists and other earthquake engineers who performed these site-specific studies and came up with the expected response spectrum at that particular site. Now we know that what is the probability or what is the spectral acceleration we would get against the fundamental period of the building. Then we selected the suite of ground motions, and we have fault normal and fault parallel. What we basically did, we basically scaled the frequency of these selected ground motions such that the geometric mean at 0.2 seconds coincides with each other. And the reason we chose 0.2 seconds is because it's a two-story building. 0.2 to 0.3 seconds is the natural period you would expect, and we wanted to have a resonance at that time. That's what the period we chose from the scaling standpoint. Then we analyze the building model in bidirectional manner so that we can also capture the torsion, if not, to determine what is the damage you could expect in a building. And that's another kind of table showing you all the selected ground motions. And then what we did, we basically took the envelope of all the load cases, and maximum from all the load cases was considered as your demand. 5% modal damping and small amount of raleigh damping was also considered. Now, the plot on your left is showing you the deformation, maximum displacement at various levels under different earthquakes. And response on the right is showing you the drift. And the drift is story shear divided by story stiffness. That's what the drift. And we are interested in more of a drift. And from the drift standpoint, you could see that all the deformations are concentrated in the first story, and the drift at the second story is almost zero, which means that the columns at the first stories are taking the whole load, and that is causing the collapse of your whole building. We also looked at the plastic rotations of the columns. I did mention that I use strain models, but I also compared the plastic rotations. I converted my strains to curvatures, from curvatures to rotation. It's a simple mathematical formula that one can easily relate. And now you could see the red line shows that all the columns have crossed the collapse prevention limit state, which on the plot on your right side, you could see that they entered the collapse region. There were few columns which were in the collapse prevention limit state, and none of the column was in life safety or immediate occupancy. In short, almost all the columns at the first stories have suffered the collapse under the selected ground motion. Now, what is the takeaway from my evaluation? I found that building behaved poorly in X and Y direction. Why? Because of the irregular distribution of infill walls along the height of the building. The second was the plastic rotation of the first story columns exceeding the plastic rotation limits stipulated in the codes under jurisdiction. And of course, when I calculated the plastic rotation, there is a role of transverse reinforcement. And that transverse reinforcement is basically confining the core of your concrete, and that would improve your plastic rotation capacity. And I also noticed there, the plastic hinge regions, the spacing of the transverse reinforcement was not enough. That could improve your rotation capacity of your columns. So what's my final conclusion? The building needs to be retrofitted. There are many retrofitting approaches available out there that could be used to improve the building performance under earthquake forces. One is global retrofitting approach. The other one is local retrofitting approach. Depending upon your desired performance objective, one can select any approach to improve the performance of the building. And in global approach, we can have infill walls, we have concentrically braced frames, and in local approach, we have concrete jacketing, FRP wrapping, and then we found that the braces have enough strength and stiffness and can be used to improve the performance of the building. So that's like a more viable approach as compared to other global approaches. Among the braces, we have found that, but one of the biggest thing I should stop here, that the braces will buckle under compression. Under yielding, it's simple, Fy Ag multiplied by a factor, that is an expected tensile strength. But under buckling, if your critical buckling load is less than the yield strength, it's going to buckle under compression, and that would defeat the purpose of retrofitting as well. So from that standpoint, then what should we use to improve the performance of the building? Then I'm going to talk about buckling restraint braces. That was my master's thesis research. I basically developed a design methodology, which I actually used to retrofit the building in the north of Thailand. So buckling restraint is basically the steel core encased inside steel tube, and that tube is filled with the concrete. What it does, it basically reduces your unbraced length of the column under compression. So you could imagine that if you are loading your column under tension versus compression, your strength stays the same. There is no buckling, as you could see from the dashed line. That is showing you the behavior of the conventional bracing system. Okay, now the design philosophy. The question at that time was, what should be the area of the core? What should be the configuration of the core that we should use that could achieve the desired objective? At the top, you are looking at various retrofitting schemes where I am telling you that you can start from a different strengths, and then that could still cause you a soft story, or you can determine the optimum strength that can achieve the desired goal. So the idea was we can't add a lot of strength at the first story that could cause the over retrofitting, and damage moves to a second story, and that can cause a collapse again. We need to have a certain level of damage, a uniform distribution of damage along the height of the building, such that we can dissipate the energy under seismic excitation. And for that, what I did basically, I equated the strength of the second story infill walls with the strength of the first story brace. And from that, I determined what is the required strength I need at the first story. And based upon that, I determined the number of braces. And from there, I determined what is the required area of the brace I need against that desired strength. Of course, from the bracing standpoint, code says you have to have at least 2 bays of the braces in each direction, and such that the removal of the brace does not cause the removal of the reduction in the capacity by more than 33%. So there are like some code nuances were there, and also the design approach was there too. And that's another way to look at, we can't just make brace too soft or too stiff. But the seismic design principle of that building was that I'm using the brace. Why? Because the brace have higher energy dissipation capacity. But in order for the brace to take that capacity, I need an earlier yielding of the brace, so that once it enters the inelastic region, all the deformation would go there and my columns would stay elastic. That's the seismic design principle. And from there, as you could see, I installed the brace in inverted V configuration in the east and west elevation, and have a diagonal brace configuration in the north and south elevation. And I attached the brace at a certain distance away from the beam column joint. Why? Because at that location, the beam column joint were not that confined. I was not interested in inducing more shear into the joint. If I'm saving the column, that can cause the collapse of the joint. That's another brittle failure. So I moved my brace at a distance away, which is E, from the face of the joint, so that I can avoid transferring the large amount of shear and tension in a column. So that was the overall approach. Here I am comparing the comparison of the story drift of two building models, have a brace and without the brace. As you could see that the presence of the braces have significantly reduced the deformation demand in the first story building columns. And on the right, you're looking at the plastic rotations where all the columns have reached their plastic rotation less than immediate occupancy limit. What that means is if an earthquake will come at that particular site, there will be an immediate occupancy stage, which means your earthquake will come, you can go back to the building again, and there will be no damage at that location. You don't even have to repair the building. So that's the physical way to demonstrate the results to the client. And the analysis did not stop there yet. What next step did we did? Because of the presence of the braces, we are adding a lot of the shear in the foundations, in the beams. So we checked that sequentially to determine the saving one thing is causing a sacrifice of the other thing. We don't want that. Client doesn't want that. No one is interested in that. So what I did, I found that due to the presence of the brace, I'm adding so much compression in these columns and also the shear. We need to improve the shear capacity of these small columns below the grade beams by adding a concrete jacketing approach. Similarly, and I did compare the shear demand to capacity ratios of all the columns below the grade beams, and just showing that in unretrofitted building, the demand to capacity ratios reduced significantly by using the retrofitting approach. Then I also checked the foundation, and my foundations were failing in bearing. What I did, I proposed using the strap beams to connect the foundation, and that would increase your bearing area. So that would basically improve your demand to capacity ratio, and also the factor of safety against the bearing, which is an overturning failure, because you have an uplift on one side and compression on the other side that would cause a triangular distribution, and that could uplift your foundation. And also, if your column is saving, the foundation can fail. No one wants that. The last step was also to check whether this beam where I'm attaching the brace have enough shear. As you could see from the plot on your left, that the shear demand to capacity ratio of the beam was exceeding due to the presence of brace. So we proposed having a steel plate on both sides of the beam and connect that brace by using expansion anchors to improve basically the shear capacity. The idea was to improve the shear capacity of those beams. And that's the wrap. That's the final takeaway. As you could see, I installed the steel plate at the portion of the beam to improve the shear capacity there. I added the brace to avoid a soft story failure. I then retrofitted the columns below the grade beams to improve the shear capacity, and similarly combined the footing around in the vicinity of the brace to improve the bearing capacity as well. So that's an envelope or overall response or overall retrofitting approach that I adopted to retrofit the soft story buildings. Okay, so that's a stopping point. Next, I'm gonna move to a different topic that is about the collapse assessment of the base isolated bridges. Okay, so that's a second topic. That topic is not a typical design. That topic is not an existing building. That topic is basically related to the forensic investigation. What happened was it is related to a base isolated bridges located in the XYZ part of the world, because when we work on these projects, we signed an agreement that we cannot disclose the location. We cannot disclose the name of the parties. As you could see on the top left, I'm calling a contractor. On the top right, I'm calling a structural designer, who is the engineer of the record. So what is the story? The contractor found that a structural engineer has made significant amount of mistakes in the design of the bridge piers, which means that these piers are going to collapse under earthquake. That claim was filed and contractor requested a significant amount of design change or an increase in the amount of money if they chose to improve the design by themselves. Both the parties entered an argument from a legal standpoint, and that becomes an international arbitration. An arbitration means there is an arbitrator in a different part of the world who would listen to the claims from both the parties and will make a decision. Now, both the parties will hire their experts. They call this, we were representing the structural design team, and the contractor will hire another expert that we call them as an opposing expert. So I am basically writing a report against the opposing expert. So what's the nuance of that problem? A quick definition here so that the attendees can understand what is a regular bridge and what is a base isolated bridge. Non-isolated bridge, of course, you will displace your bridge pier or a bridge under lateral loading. You would expect the plastic hinge formation at the base of the column. The design stand would say, I will add a closely spaced transverse reinforcement so that I can have a ductile mechanism. In brace isolated bridges, the column stays elastic under seismic loading, but we will add the bearings below the superstructure so that there is no deformation in the columns. So contractor found that the structural engineer designed your bridge pier against an incorrect value of response modification factor. And we know I can imagine all the attendees on today's lecture and the people who are listening to me know that response modification factor is an important design parameter for the seismic design of the buildings and bridges. Higher the response modification means that this building or bridge have higher ability to dissipate the energy. Contractor found that the design engineer designed a bridge for an incorrect value of R, where the bridge code says you cannot exceed more than 1.5 for a base isolated bridge. Contractor filed a lawsuit against a structural designer and said that due to this incorrect value of R, it will compromise the structural safety and could lead to a collapse. The picture you are seeing is basically the analysis conducted by the opposing expert, where he found that all the bridge columns were failing. And he simply compared MU with VMN. And then he's, as you could see from demand to capacity ratios, they were exceeding the design moment strength. And he said that he designed for an incorrect value of R. That incorrect value of R is leading to a smaller forces, which is not true. The real forces are higher and that are causing your bridge columns to collapse. So this is not acceptable. That was his claim. That drawing came to my team. I looked at the drawings. I looked at the analysis model, and then I chose to adopt the risk assessment approach to determine if contractor is saying that if we construct that bridge with an incorrect value of R, whether this bridge will collapse, yes or no. I chose the probabilistic approach to find out the answer. Let's dive in. I selected 80 ground motions for that particular site, developed an inelastic mathematical model that can capture all the important aspects of that base isolated bridge, and then I scaled the intensity of each ground motion such that it reaches the collapse level. Once I have the drift at the collapse spectral accelerations, I use those drift levels to determine and develop the fragility curves. Fragility curves will tell me what is the probability of collapse under a given value of seismic intensity. Then I integrated that with the hazard curve. Hazard curve means what is the likelihood of that particular earthquake on the site? Easy way, what is the return period of that earthquake? And then I would determine the mean annual frequency of collapse. Okay, so what I found from this analysis that bridge have significantly achieved the desired capacity to avoid the failure, which what that means is I'm trying to make that simple for the audience because I'm unable to share the exclusive results because they are very confidential. Hence, I basically drawn a schematic so that the attendees can understand the steps and the process that I followed and kind of convey the result. So based on my fragility curve, I found that the bridge probability of collapse is less than 1% under an earthquake with 2,500 years of return period, which means that if that bridge would have constructed with that design engineer was used, the bridge would never have been collapsed. So that was my finding. And the takeaways are the opposing expert argued that the piers were at the risk of collapse. He has effectively chosen the performance limits that were inapplicable to the bridge piers. To conclude that a code deficiency is equivalent to collapse risk is to ignore the degree to which structural element may be deficient. Now, I'm not saying that if your design engineer or your younger staff found that my MU is greater than PMN and you go to your boss and said, Dr. Tariq said the building is not gonna collapse. You should not avoid that. But I'm saying in that way, you should need to supplement your analysis with the performance-based analysis by using the earthquake, seismic ground motions, and then determine what is the risk of your collapse. And from there, I found that the bridge is not going to collapse and it has a significant reserve capacity. Of course, if that structural designer designed an earthquake for the lower lateral forces, he also provided the plastic hinge. He also detailed the plastic hinge locations of the pier such that they could take all those seismic excitations. So the end result, the case was settled, we won, and the adjudicator, they liked the approach we adopted. Okay, so I'm gonna move now to the next step, which is basically the challenges in a high-rise building. Now, this is not related to an earthquakes, but it is related to more of a challenge. So again, I'm bound not to disclose the location of the building. One day I will, if I ever once I will go there and take pictures and my name would be there. But I'm gonna say it's a building that is its construction has started, located in New York, Manhattan. It's a building and unique in its own ways. The unique in a way that the owner of that building wanted the building to be exposed. What that means is there will be no false ceiling that can let your pipes go through. The columns concrete will be exposed. You will see the classic feel of your concrete with the friction. And of course, it has many other challenges. If you have no false ceiling, which means that all the MEP penetrations will happen within your beams. And if you are taking the block of the concrete out of your beams, that's going to reduce the stiffness at that location. And there are stress concentrations and the beam can fill down there as well. So that's another schematic of your 3-story building that shows the building have a significant amount of a cantilever in the north-south direction. It's a building frame system. What that means is the lateral loads will be resisted by a shear wall around the elevator, and the columns and beams were designed to take the gravity loads. And the building design was governed by creep and shrinkage. Now, by looking at this picture, you could see that under the action of the creep, this portion of the building is much heavier that will lean towards that side, and there will be an axial shortening of the column. And if there is an axial shortening and you have not considered that in your design, it will also kind of cause a punching shear failure of the column. And you could see that we only have 2 columns in that 30-story building. So failure of 1 column will reduce your degree of redundancy significantly and cause kind of collapse. So, but I'm gonna tell you here that the building design was basically dictated by creep and shrinkage limits, and the deflection at the tip of the cantilever was significantly high, that they were exceeding the joint size of your facade. Now, that's a 3D building model on your left, and on your right, you're looking at an exaggerated picture of the small portion of the building. That's another way to look that our cantilevers were significantly high. And of course, one could say that the stiffness is 3EI over L cube, and that's going to cause your significant amount of deformation. And also the loads were very high as well. So here you could see that the client wanted to have a green terrace on each floor, and the client was not interested in a green carpet, which we can buy from the stores now, to fake your grass. He said he needs a 3 feet soil at the terrace level. The 3 feet soil means 80 PCF, which is a soil density multiplied by 3 feet. You're getting a significant amount of superimposed dead load at the location of the stairs, at the location of the terraces. And on the right, you are looking at the plan view of one of the floor. And live loads are significantly high. So what was the challenge here? The challenge was basically the joint size of your facade. What is facade? As we know, we probably in Islamabad, I remember Blue Area, the Ufone Tower, or a Park Saudi Tower, and many high-rise buildings, you would see the glass panels in the perimeter of the building. The contractor will attach those glass panels to your structural elements, and he has to accommodate a certain level of deformation within that joint. And he doesn't want to increase the joint size because he wants people to see the shiny glass. So if you are walking or driving by that building, you will see exposed things and fancy lights. You would be like, wow, this is such an amazing building. You want to walk inside or go, or maybe buy an apartment if your wife convinced you to do that. So it's an architectural thing here. So that's the size of the joint. As you could see, the joint size was 1 inch, and we are having a significant amount of deformations, and that deformations were exceeding the joint size. What that means is they would cause the damage to the glass. You could see that glass would fall off the building because the deformations exceeded the size of the joint, and that will cause the failure of your facade. So what I did, I basically determine what are those critical locations, which were several floors. I tied those several floors with the steel tie. The steel tie, I basically did, I'm going to show you from a mathematical standpoint. I considered that these floors, which are critical in nature, but that means which are going to have a large amount of time-dependent deflections, and which are exceeding your joint size, should be connected by a steel tie. And how did I determine or design the steel tie? I considered that these frames, cantilever frames, are behaving as springs in parallel, where the total stiffness is equally to the summation of the stiffness at these 5 through 8 levels. And then I added a tie. What the purpose of that tie was that these 4 floors will deform under gravity load as a one rigid unit. So there will be no differential deformation, which means that all the joints will move up and down at the same rate. So that would reduce your deflection significantly, and that would solve the problem. Now, that was a mathematical way to explain the problem. Also, from the constructability standpoint, you want to tell the contractor that what you envision, how are you bringing that theory or science onto the from piece of paper to the ground. So this is a quick snapshot of what we designed. We have a shear studs to take the shear. We also attach that tie, which is an HSS circular column with the embed plate of your spandrel beam, and have a steel rebars at the 5th floor, and the same scheme applied at the higher levels. So yeah, that's the final takeaway. Section size is often limited by architectural requirement. That is true. Sometimes we think that the beam is 18 inches deep and the architect says you can't go more than that, but you need a 24-inch deep beam to achieve your required moment of inertia so that you can get the deflection. That is not going to happen, because the client wants to see a clear spacing. Client wants to see a thin slender columns. Long-term deflection is the biggest concern in the cantilever slabs. That's true. If you are not considering the long-term deflections, after 10, 20, 30, or 40 years, it's going to cause a crack in your concrete. The water will creep in. It's going to corrode your rebar. It will compromise or jeopardize the structural integrity. You could also use the post-tension beam system. You can use the steel plate girders within that beam to achieve that desired goal. So what did I talk today? I talked today 3 different things. One was a code-based design. What challenges one could imagine? There were many challenges, but today I presented you with one basic challenge related to time-dependent deflections. Second, I talked about performance-based design, where what approach you need to adopt to retrofit the soft story building, and how would you compare your deformation demand with the deformation capacity? And third is a risk-based design. And risk-based design, the idea is basically to determine what is the risk of collapse of a particular bridge at that site, so that you would know, if I am designing that particular bridge or a building, what is the likeliness that this bridge would collapse. So that concludes my presentation. I hope you guys like it. If you have any questions, please let me know.
Thank you, Dr. Tariq. A very wonderful, informative lecture. And I was really impressed with your slides, the way it worked. It was really, very
Thank you, sir.
the slides are really good. So if, ladies and gentlemen, if you have any questions, you can type them in the chat box, and I will read them for Dr. Saab to answer. If there are any questions, we have 20 minutes, 20 to 25 minute session. So let me see if any question has been typed. No. Rizwan, do you want to say something? Rizwan?
It's very fine, very well delivered, very well researched talk. I think everybody must have benefited from it. You already summarized it very well. Thank you.
I mean, the slides were, I was really impressed. His talk and his slides were working in harmony with such a nice coordination. And though it is not my subject, but I have studied structural dynamics in my master's. I could understand a lot of what he has said. And I hope the participants have also enjoyed the lecture and have learned. Yeah, somebody's writing very needful and informative. Can I get? Yeah, one thing, Dr. Tariq, we have recorded your lecture, and I hope you don't have a copyright problem. Can we upload it on our website?
Yes, you can.
Okay. We have one question from engineer Ijaz Ali. He's asking, my question is regarding the bridge design. what was the main purpose behind objecting the design of the bridge by the contractor? Did he want it just to increase the cost?
His claim was that the incorrect design, according to him, will compromise the safety of your bridge and will cause the collapse. So he was letting the owner know that this incorrect design will cause the collapse of your bridge and compromise the safety. We should not construct that bridge. If you would like to construct that bridge, we need to redesign the bridge piers by using a lower value of R, which means a higher shear forces. Higher forces, higher steel. Higher steel means higher capacity, and that would balance out the equation.
Yeah, I think Ijaz was asking that since with the redesign, I mean, if you had accepted his plea, the cost of the bridge would have gone up, and that would have benefited the contractor. This is what was his intention of.
Did he just wanted to? Of course. I mean, in United States and all the other things, I mean, why would I do such business where I'm losing money? I want to tell the owner, this is incorrect. I can't take risks. Had he constructed the bridge, what if bridge collapse and this would be on his neck? So he wanted to alert the owner that I'm not doing this. But we took a different route and tell the owner he's not doing this for his own reasons, but from a scientific standpoint, this bridge is not going to collapse.
Any more questions? I'm waiting for the questions. And there's one, if you, we don't have any questions yet. If you want to say anything more, please do so. It is your subject also.
Okay, there is a comment, not a question. This regards to it is with respect to the test that was applied to determine if the design was safe. A probabilistic analysis was conducted, as you said. According to my understanding of the law, if somebody designs something as his or her peers would under similar circumstances, he or she is not negligent. You cannot apply an unusual test to determine if the design is safe or it is not safe.
That is totally true. But he was saying that this incorrect design is going to compromise the safety of the bridge. We agreed to his claim that this incorrect design is going to affect a level of damage, but does that level of damage is going to compromise the safety of the bridge? Because of course, you look at this figure, you see that my demand is significantly higher than the capacity. But the idea was, does that higher demand is going to cause the collapse? We agreed to his stance that, of course, there will be the damage in the bridge piers, and that damage may cause a cracking, that damage may cause a yielding, but that damage is not going to rip apart your core and turn your whole bridge upside down. So that's how we rebutted wrote a rebuttal report in our response. And I agree with you that we were not questioning his approach. His questioning approach was correct. If I am a reviewer, I would adopt the same approach to check whether it satisfies the code provisions, and I would write that report accordingly.
Thank you. Thank you.
Yep. Dr. Saab, your lecture was marvelous, very much coordinated with your talk, and your slides was really very well coordinated. I think you went a little bit fast as far as I am concerned. People are taking time to what all you have are taking time to assimilate what all you have said in such a short time. So now the questions are pouring in. So
I mean, it's good that they listen to the things. When I used to hear the presentation when I was at NASC, no one would ask the question because the topic would be difficult to understand.
The general trend here is like this, but now Pakistan society is really working hard to inculcate this sort of tendency in the engineers that they should come up and ask, they should be asking questions as much as they want. So let's say it's engineer Muhammad Inam. He is asking types of software you recommend for a structural or earthquake engineer being an initiator or a basic learner. Before Dr. Tariq answers, Inam Saab, let me tell you that softwares are good, but it is the person behind the software who matters. Dr. Saab, please answer.
I'm gonna second your thought. You know, I preach this thing to every structural engineer that you need to have the ability to transfer the load from the roof of a 40-story building all the way down to the foundation by your hand. If you cannot understand the load path with your hand, the software is just a black box. You put garbage in, garbage out. You understand the mechanics. Software is to back check your results that you have learned this, you have developed that, and that's what you are getting from the software to confirm your understanding.
Okay, thank you, Doctor. Now we have a question from a participant who is on Facebook. He is Junaid Shah. He's asking how to idealize the masonry wall in bare frame, which is the basic frame, which is the best macro modeling approach of defining the diagonal compression strut in order to idealize the infill wall.
I think compression strut, I should have said you would draw a line element. That's what it is. I also gave a reference at the bottom. Masonry infill wall model, an article by DeKine, 2004. So the attendee can download that paper, and there they have explained the methodology that how you should connect the struts. This is basically a line element. And within the line element, you basically have, as I say, the nonlinear behavior of the wall in each direction. And then you would assign that to the wall line element, and that would simulate your behavior.
Now we have a question and a comment from Hamza. Hamza has just commented what I said. He's saying, Sir Tahir, not. Somebody did not mute his mic. I have done it. Okay. The question and a comment is from Muhammad Hamza, and he has commented on what I said. He is saying, Sir Tahir, not fast. It is a very brief and interesting presentation. Just a comment. Oh, very nice. If you liked it, if it was not fast for you, maybe I have become old and it was a little bit fast for me. But anyhow, very interesting. The question is, Dr. Saab, RMF has direct impact on ability to dissipate the energy. What is maximum limit of this RMF?
So I presume you are saying reinforced moment frame. We have three different types: ordinary moment frame, intermediate moment frame, and special reinforced concrete moment frame. Depending upon your seismic design category, which means the risk of the building at that particular location, you will determine the moment framing system. That particular building was ordinary moment frame. The reason is that in Thailand, people don't think there will be an earthquake, but that location was close to Myanmar. And the earthquake that would travel from Myanmar to that part of the Thailand is basically the aftershocks. And that aftershocks could cause the damage that have caused the damage in the past as well. For an ordinary moment frame, you would go to the ACI code and they would tell you that you need to confine the potential plastic hinge regions. Basically the detailing, the idea is detailing. Anyone can come up with the longitudinal steel, with the transfer steel, but how are you dissipating the energy? For this, you need to determine that what is my seismic design principle there. If I'm saying I am considering a moment frame system, am I allowing all the columns to yield or just the perimeter columns to yield and the interior columns to design for the gravity? So I think a smart design engineer would think, I think I'm not gonna just increase the size of all the columns, I'm gonna make the perimeter columns as a large squares, and then I will have all the interior columns take the gravity loads and call it a day. Other one would argue and say, I think I'm going to use a 2 base of the moment frame, or maybe add a shear wall and take all the column as inelastic. So that shear wall is a shear wall system where shear wall will take all the loads, and their limits are stipulated in way of adding a transverse reinforcement in boundary regions, confining the boundary regions, development lengths, and the entire design process.
Thank you, Dr. Saab. Yes, audience, if you have any further questions, please type them in the chat box. We still have 5 minutes more. Huh? You have? If you can see the chat box, Hamza is saying thanks to you, Dr. Saab. And
My pleasure is all mine. If no one has a question, I will say something that after so many earthquakes have happened, and wherever I go, wherever I always tell the structural engineers to have a belief in yourself. You know, I was invited at the gathering of the real MBBS doctors at the hospital, and I was talking to a program director, and I said, you know what? If the doctors are saving one life at the time, structural engineers are saving hundreds and thousands of lives. Every time the earthquake comes and bridges don't collapse, that's a structural engineer holding it inside. But every time the wind blows and buildings don't fall apart, that's a structural engineer holding it inside. And that's the noble profession humanity has ever created. So he was a smart guy. And he said, well, I bought your argument that if I'm saving one life at the time, you are saving hundreds and thousands of life at the time. I agree with that. You won one, my point is 0. But if you are designing a poor building, you're also causing the life of 1,000 people. If I'm killing 1 people, you're also killing 1,000 people with your poor design. And I was surprised to hear that him saying this, and that is true. Being a structural engineer, we need to understand our responsibility in a society, that we are responsible for the lives of the people. We are not just simply designing the beams and columns. We are adding value to the society. That's why we are called as civil engineers. And every structural engineer should step up and take the responsibility and add value to the world and to make it a safe place.
very well said. Very well said. I was just, I also had the same views, you know, a few years back. I don't know, Dr. Saab, you remember, earthquake came in Japan. I think it was of the intensity more than 9 on Richter scale, 4 or 5, and not a single building collapsed. The cracks were there, but not a single building collapsed. And few roads, I think there was some cracks on the roads and bridges, but nothing collapsed. And that is the standard of structural engineering in Japan. Most probably, I think they have done also a lot of work on earthquake. Earthquake is their problem also. So they have done a lot of work.
Yeah.
We have a question from Mr. Hamza. He's asking, Doctor, please also give some regard to geotechnical.
Of course, I mean, with structural engineering, I said the engineering community as a whole, of course, without geotechnical engineering telling us the right bearing capacity, how would I design the foundation? If geotechnical engineer is not telling me there is a liquefaction, how would I design my pressure slab? So of course, geotechnical engineering is there too. And I want to say the success is a team sport. In order for a successful project, the team has to contribute. There is a structural engineer, there is a geotechnical engineer, there is a construction engineer sitting on a site telling you all the things, and there is an architect. So the success is a team sport that all the teams have to well coordinate to deliver a valuable project.
Yeah, Hamza, Hamza, I am a geotechnical engineer myself, and I really tell you that all the engineers, structure engineers and geotechnical engineers, they give the importance to the soil engineering. And soil engineering still, as compared to structure, is not developed to the same level. It's not 1 + 1, 2 as it is in structure. There are a lot of empirical equations, empirical things which we are using in geotechnical engineering, and it's more important in the structural design, especially in the seismic zone. Geotechnical engineering has to play a very important role there. Anyhow, thank you very much, Dr. Saab. A very nice lecture and a very nice talk and comments. And audience, thank you very much for your deep interest in this topic by asking the questions. Rizwan, thank you very much for your comments. So now we have to end the lecture here, and let me make some announcements for the audience. The next lecture is on 13th May, and the topic is design of concrete slabs and introduction, and our speaker would be engineer Rizwan Mirza. So it is 13th May 2023. Dr. Saab, your shield and your certificate, inshallah, will be dispatched by Ms. Sadia in the coming week to your address, which you have given to her. And from Pakistan Society of Civil Engineers, we shall be giving you a free membership of the society.
Thank you, sir.
And we will expect that you will contribute something in the society also.
Absolutely.
I'm 100% sure you are an American citizen of Pakistani origin, and I hope you will remember your country and the society.
Absolutely.
And inshallah, we will have your input. Incidentally, Rizwan Mirza is the editor-in-chief of our publication board. If you have anything to publish on our forum, so you can always contact Rizwan Mirza, and you already have a introduction with Sadia Naveed. He will be there to assist you in whatever way you need the assistance. Okay, so this was for Dr. Saab, and for the audience, you can collect your certificates from 20th May from our office, which is 14A1 Block P, Model Town Extension. And the person to contact is Ahmad Akram. His cell number is 0347 462 5111. And still, if you have any issue on our website, our how to contact the society and how to contact Ms. Sadia, the details are given there. So with this, we come to the conclusion of this session. From Pakistan Society of Civil Engineers, what is it? Yeah, that's okay. So from PSCE, I wish you a very blessed remaining Ramadan, and wish all of you in advance Eid Mubarak, and thank you very much for attending this session. God bless you all. Okay.
Thank you, sir. Allah Hafiz.